It's a force that governs the universe, from the spark of a single thought to the storm in the sky. It's the invisible current that powers our civilization. But to truly master this force, we must move beyond simple flow and understand the fundamental laws that govern it. This is the story of electrical physics, a story written in charge, current, and field. It all begins at the atomic level. The key players are the proton, with a positive charge, and the electron, with a negative charge. Normally, they balance out. But when electrons are transferred, like through friction, the balance is broken, creating static electricity. This imbalance creates an invisible, powerful zone of influence, the electric field. This field is the true mechanism of force. Any other charge placed within this field will feel an attractive or repulsive push, acting at a distance. The strength of this push or pull is precisely calculated by Coulomb's law. It tells us the force between two charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. It's this fundamental law that quantifies the attraction and repulsion we see. Static electricity is a snapshot of potential. To create a continuous usable flow, we need current electricity. This requires a closed pathway, a conductor, like copper, which has loosely bound free electrons that can move easily, and a push, which we call voltage. The relationship between these three is the cornerstone of electrical engineering, Ohm's law. It states that the current I flowing through a conductor is directly proportional to the voltage V and inversely proportional to the resistance R. Understanding this relationship allows us to design circuits that do exactly what we want. Not all current is the same. Direct current, DC, from sources like batteries flows steadily in one direction. Alternating current, AC, from wall sockets constantly changes direction, typically 60 times per second, 60 Hertz. This oscillation is what made AC the winner for power grids, as discovered by pioneers like Nikola Tesla, because it allows for efficient long-distance transmission by easily stepping voltages up and down. But what if we need to store this potential energy briefly? Enter the capacitor. This clever device stores electrical energy directly in an electric field between two plates. It can release its stored charge in an incredibly rapid burst, which is why it's indispensable in camera flashes, computer memory, and tuning radios. Perhaps the most profound discovery was that electricity and magnetism are not separate forces. They are two manifestations of a single, unified, electromagnetic force. A changing magnetic field creates an electric current. This is electromagnetic induction, the principle behind every electric generator and power plant in the world. Conversely, a changing electric current creates a magnetic field. This is how electric motors work. This deep connection is why the most advanced technologies, from the grid that powers our cities to the MRI machines that save lives, are built on the principles of electromagnetism. From the quantifiable push between two charges, described by Coulomb, to the predictable flow of current, governed by Ohm, the invisible river of electricity is not a mystery. It is a science. By understanding its language of fields, forces and flow, we don't just use electricity. We converse with it, harnessing its laws to shape the modern world.